So let's use polyfit to find the line that best fits our data. So what we've done here is create a new Python procedure called fitData, and it's just like plot data, except that we've added a call to polyfit, in which we give it the forces and the observed extensions and ask it to find the equations of the line so that the predictions best fit the observations. Then we go off and use those parameters to make a bunch of estimates for what the y value should be, the extension should be, based on the forces that we're applying. And here we're using the predictive power of our mathematical model, and we're going to plot that line on the graph. And finally, since the slope of the line is 1 over k, this is the slope, so that means that k is equal to 1 over the slope, and we'll also put that on our plot. So let's go off and run this procedure on the data values. So I've already saved this out, so we'll start the execution, and hopefully up will plot. Here it is. And here's the line. We can sort of see it here. And you can look at that and say, well, okay, that's the best fit line, I suppose. It does the best job it can of sort of minimizing the sizes of the squares of the errors here. But it doesn't look like the best fit. It seems something here but we don't like. Maybe Hooke's law is wrong. Maybe there's a different curve here that would actually fit the observed points better. So just for grins, let's try to invent Terman's law. So what Terman's law is, in fact, that there's a cubic relationship between the force that's applied in extension rather than a linear relationship. So let me start off by commenting out the call to fit data. And here I have a new procedure, fitData1, which uses polyfit to fit a cubic equation to the observed data. And let's plot those results. So I'm going to make it so we run this guy, and I'm going to save him out and then start execution. And here's the resulting plot. And in fact, this actually looks better. Maybe Terman's law has something going for it here. It looks like the curve looks much closer to all the points than the original linear fit. So maybe Hooke got it wrong, and modern springs are much more sophisticated. They obey the sort of cubic relationship between the force that's applied and extension that's observed. Well, how do we figure this out? I mean, here we fitted some data, and we're sort of saying, gosh, it certainly looks like that's a better fit. Well, one of the ways we can evaluate the power of a model is its predictive power. So what I want to do, I'm going to start by, let's comment this guy back out again, and look at fitData2, which is just like fitData1, except what I've done is that when I'm going to use the model for predictions, I'm going to ask it to predict the extensions created by applying heavier weights. We didn't make these measurements, but we sort of expect the spring to keep stretching as we apply higher and higher weights to it. So everything's just the same. We're still doing a linear fit here and a cubic fit here. Let's see what happens when we run this and plot the results. So we're trying to use our model here to determine sort of the predictive power of Terman's law, which hypothesizes a cubic relationship between the extension and the force applied. So we're going to save this out and then run it. Here's the results. Oops. We did a pretty good job of matching our curve to the observed data, but when we went off and asked about some predictions, so here's what the predicted extension is as we add additional force to the end of the spring. And even though we're pulling on the spring harder, all of a sudden the extension is getting smaller and smaller. The spring is no longer stretching, it's shrinking when we pull harder on it. Well, gosh, that doesn't seem quite right. So even though we've managed to find a way to fit the curve to the observed data, it turns out the predictive power of Terman's law is bunk. It's simply predicting behavior in a spring that doesn't seem very sensible, and we would certainly expect displacement of the spring to continue to get longer as we pulled on it. So let's give up on Terman's law and actually think a little bit about what we saw in the data. So when we looked at the data, what we sort of saw that it sort of flattened out at the end. And so what I was thinking of is well, actually, let's put that plot back up while we're sitting here. if we look at this sort of flattened data here, we can see the curve sort of flattens out at a point. So it looks like Hooke's law may, in fact, with some observational error measurements, errors in our measurements that we made, it looks like Hooke's law might be okay. It's just that these last data points show that the spring has stopped stretching. And we might hypothesize, instead of Terman's law with the cubic relationship, we might just say, look, Hooke's law applies up to the point that the spring reaches its elastic limit. In other words, when it stops behaving as a spring and now just behaves as sort of like a rigid a rope or a cable of some sort. In other words, it doesn't get any longer just because you hang more weight on it. So maybe what we should do is try getting rid of these last points and seeing if Hooke's law does a better job of doing the prediction. So we're going to come back here and go ahead and comment this guy out and look at fit data 3, which is just like fit data 1, except that what we've done is to eliminate the last 6 values, the values that we feel that correspond to the spring having reached its elastic limit. So let's go ahead and run this. So let's comment that back in again, save that and run it and see what the plot produces. And voila, this is, without that flattening out of the curve, we actually have a fairly good fit to the data. In other words, the errors now have gotten, there's still some amount of measurement error, but now the curve seems to fit better. And in a couple minutes we'll talk about what a goodness of a fit, a measure of the goodness of a fit. But we're pretty happy, or certainly happier with this fit than with either the cubic fit, which mispredicted, or the original fit, which just didn't seem to fit the points at all. So this sort of raised the questions, are we just sort of allowed to eliminate points we don't like? I mean, suppose I eliminated all but 2 points. I'm going to keep this point and that point, and then I would discover that I can make a perfect prediction. Well, you can always put a line through 2 points. So why was it I sort of felt comfortable eliminating those last 6 points, and I'm not running around eliminating some other points here that seemed like sort of embarrassments and are making it harder for me to show that Hooke's law is the right equation? And the answer is, well, I had a theoretical justification. I hypothesized this notion that there was an elastic limit to the spring, and as soon as I saw that the length wasn't growing as I added extra weights, I said, okay, maybe what I should do is to consider that a different regime. Hooke's law wouldn't apply there. But I am expecting Hooke's law to apply for all of these measurements. So I'm not allowed to willy-nilly just get rid of points that I don't like. I really do need a theoretical justification. But with that justification in hand, I think we can make a fairly good prediction that the spring constant of the spring is somewhere around 15.5, pretty close to 15.5.